In this video, we're going to look at how we have created a virtual kernel for our software code base. And this is essentially a virtual operating system. It is a set of interfaces that wrap and obfuscate all of the actual details of the platform so that it could be implemented on different platforms. And we can write to a generic API that will not change. And there are a lot of issues, as you can imagine. And we will look at some of those here and how we've done that. This is all C++ code, of course. It is a part of a large code base of about 1 million lines, and the bottom half, they're about equal size, and the bottom half is about 500,000, and it's a general purpose layer, and that's what we're going to look at today. And the top half is a home automation platform called CQC, which is built on top of the general purpose layer. So we're just going to look at how we implement our virtual kernel. And we're going to start first by just looking at a sort of a diagrammatic view of the of how all the general purpose code is laid out, and that will kind of give you some perspective as to where you are when we're looking at some of the code. So here is a image of a sort of a diagrammatic image of the system, and basically at the bottom, of course, there's the operating system. And that's where everything starts, and we need to encapsulate that. And we do that by creating this virtual kernel layer here. And this guy effectively wraps all of the operating system functionality, or at least all that we provide access to. And it, of course, by necessity, because there are a lot of bootstrapping issues, it's fairly primitive. Our actual runtime libraries are implemented up here at this layer. So all of the strings and memory buffers and collections and all that stuff. And so we can't use those down here. So effectively what happens is that for each of the classes down here that wraps some sort of system service or capability, there's another class up here that wraps that one and basically makes it available in a more useful way that can use all of our public sort of runtime interfaces. And so that's one of the many bootstrapping issues. The other thing that happens down here is that we have to obviously split out each of these classes. There's that part that can be done platform independent, and that includes the actual interface, the header stuff. And then there's the stuff that can only be done on a per platform basis, and that has to be split out separately. And then there's some stuff in between that can be done generically, that because it can be implemented in terms of the per platform part of it, right? So that's another sort of bootstrapping issue that happens down in here, which we'll get into. And as I said, this one is the actual sort of public face, and this is where really applications begin to use our software interfaces. And this one has all of the runtime, the general sort of runtime stuff you'd expect, and plus the wrappers for the stuff down here. And it's important to understand that we don't expose outside of here, and with some exceptions up here, which we'll talk about, we don't expose any system headers or any language runtime headers or anything like that. So everything at this point, up more or less, is within the scope of our own interfaces. So there are a bunch of libraries, and over here, basically, the reason these are shaded is because these also contain a little bit of platform code. They are not down here because, of course, the more stuff you put down here, that means that every single application that uses our system has to pay the price for that in terms of its size and the various maybe possibly optional operating system libraries that need to be installed and stuff like that. So we need to be kind of careful about that. These tend to be a bit more specialized, so they are split off separately. For the most part, they are things that are like these three, which are the graphics, the basic windowing system, and more advanced windowing system stuff. These we don't really, I mean, although everything is encapsulated and all of our stuff is written purely in terms of our own interfaces, we don't really try to make this platform independent. That's very difficult for UI stuff, but it is wrapped and it could be done. And the other stuff is just more specialized things. Database, a lot of things don't need databases, data, digital audio stuff here, so ripping CDs and that kind of thing, speech recognition, various audio streaming capabilities, metadata extraction for media stuff, that kind of thing. Maybe some applications would use that, some wouldn't, and some of these may require optional features to be installed, so we kind of separate those out. And so these are kind of split up in the same way as these classes down here are. And mostly, though, they are still capable of using all of the sydlib layer stuff, so they're not nearly as primitive, but they will occasionally go down to either directly access kernel stuff, or they will access some operating system stuff themselves directly. And there are a couple things up here. These two actually depend upon one of these. So that means that although they are themselves completely abstracted, they would not be available unless this particular one here, which is the secure channel stuff, which is basically public key encryption stuff. And so, and this one is the implementation of WebSockets, and this one has our stuff for HTTP, SMTP, that sort of stuff is in here. And obviously that stuff is going to use secure communication, so they do depend on this one. So there's some argument perhaps for moving this down into here, but currently that's not done. We'll look at this. We'll look at how this one is split. But basically it just means that these, if they want to be available on a particular platform, they need to have their per platform version done for that particular platform. Currently, there's only the Windows version for these, and as is the case down here as well, of course. All this stuff over here is completely in terms of our own interfaces. So once you get this stuff down here done, all of this comes for free. And there's a lot of stuff here. COM ports, XML parser, regular expressions. This is sort of a basic object database, PNG support, zlib, JPEG. This is compression, of course. What else here? We have cryptography stuff, our orb stuff, which we dealt with in another video, which I'll link to. UPnP and socket stuff is all here. And then there's some very high level ones here, which are our macro language, which is called CML. And this is the engine which provides the runtime and the virtual machine and everything. And this is the debugger engine, which provides the debugging capabilities that can be embedded into an application if you want to support macro debugging and editing and that sort of thing there. And then there's some common applications up here, and mostly these are related to the orb. These are common things common servers that that can be used by distributed applications to exchange information and that sort of thing. All right. So that's basically the layout. And so next we will take a look at some actual mechanisms for what we do down here in the kernel layer. So let's take a look at some code here. I have the general purpose section of the code open, and let's take a look at SID kernel. And we can see here there are a couple of platform implementation layers, which we'll look at. I will say that the Linux one is very old. It hasn't been used in a long time, so it is not active currently, but this one is, and this is the one that we will look at. And you can look through here, you can see that these classes, a lot of them very much directly relate to sorts of things that the operating system will provide: console access, events, files, file system. Let's see here, what else we got? Modules, which are libraries or executables, mutexes, processes. Let's see, counters and semaphores, sockets, all that kind of stuff. So all of those classes are things that are wrapping operating system functionality. We have a smaller set of things. As I was saying before, this is a very primitive interface, and we need some way to exchange data with the next layer up that wraps it. So we have some very basic sort of data structures here, and this is sort of the bootstrapping process. We have a basic string class. We have I think there's a KV pair, key value pair, a linked list, and I think a hash table, a hash map. So those are the things that we can use to exchange data, mostly to pull data up and give it to the next layer up, but also sometimes to pass data in. But basically what the primary issue that we have here is that we can have a interface that's the same, but we need some way for each platform to have their own sort of storage space for each one of these wrapper classes. And we do that through a set of handle classes. So if we look at, let's see if I can find it here, handles. So we have this set of classes here called handles, and each one of them this is the public interface for them. And each one of them has just a little bit of functionality that's required. And then it has within it a per platform handle implementation class. And these are just forward referenced. So at this level, they're just opaque, and each per platform layer will allocate one of these appropriate for himself. And for the Windows ones, these are very simple. Mostly they just have a handle, an operating system handle. That's all we really need to keep up with. But on any particular platform, it could be various other bits of information that it needs to track. So if we go look at in the Win32 section here, and it's called Platform Internal, I believe. Yeah, so these are the actual internal implementations for Windows, and there's not very much. Mostly we just need to track the handle for the guy. And that's all there really is for these, but there could be much more. Now, in some other types of scenarios where we're not actually wrapping an operating system function, but something else sort of higher level, then we will do something slightly different, and we'll look at one of those examples as well. And also, while we're down here in the 32-bit section, you have these various platform headers here, and these are basically allowing each platform to define certain things. So we have some constants that might be platform specific, and those are defined here. And we have some defines and includes, and these includes are just used internally within the kernel platform layer itself. And then we have some internal helpers and that sort of thing. And if we look at, say, let's go back up to the open part here. Let's say look at an event. So this is, let's look at a mutex. So this is just the kind of the standard sort of mutex sort of thing to lock. So if we look at the public API for that, it's fairly simple. It provides the information that we need to manipulate a mutex, and it has a private guy that can be used to create a named one if they need it. And then we define one of our handles here, and everything else is basically per platform. So if we go down to the Windows part of that and look at a mutex. So we implement our handle. This is our mutex handle. And then we also then implement all those functions or all those methods in response to calls that obviously we'll do things in terms of Win32, right? So it's fairly straightforward how all this stuff works. And of course, at this level, we're dealing with operating system stuff. There aren't really exceptions. So everything down here works in terms of, well, there are null exceptions, but that's a separate thing. It doesn't throw exceptions for itself. So we basically are just always returning true or false. It worked or it didn't work on any given platform. If they did happen to throw exceptions, they would be responsible for catching and returning a status, good or bad. And that just keeps things simple and straightforward for the next layer up. So it doesn't have to worry about exceptions. It's always just dealing in it worked, it didn't work. Okay, so that is basically how this part of it goes, and everything else is just more of the same. In some cases, there will be the ability to do some work at the platform independent level because it can be implemented in terms of the underlying per platform stuff. And actually, as a Scale 2 Virtual 1 Stonehill, we'll look at one of the higher level libraries that gets split out like this, and we can see how that works there too. And the one we spoke of earlier was the secure channel thing, so let's look at that. Of course, and within these, there is also other stuff like these things. These are not per platform, not platform specific. These are just general code, but it does include this bit here, which is platform specific. So for this one, we basically forward declare a structure, and because there's not a handle per se in this case, we could have just said it was a handle, but in this case, we just, once we get out of the kernel, we kind of get away from that, always thinking of everything in terms of a handle, and just make it a structure. And we could have done that in the kernel as well. Of course, it really is ultimately the same thing. So we have our interface here as before, and then some data that would be useful in no matter what the platform. And of course here, because we are up above the kernel layer and up above the stdlib layer, we can use standard strings and buffers and all that kind of stuff. So it's a lot simpler up here. But then if we look down at the Win32 side here, we can see that platform structure is defined here, and we can store any information that we need in there, right? And then we just implement those calls. If we go back up here you notice that there is a CPP file for this one as well. And if we look at that, we can see that there is some stuff that can be implemented in terms of the underlying platform-specific stuff. So there's a received data that is very generic, and we can implement various read methods in terms of that one. So we don't need to push all this stuff down to the per platform. And obviously, if you really were going to start porting something like this, you really want to minimize the amount of per platform code that you have. So that's basically it in a nutshell. I mean, we could go on and get into more detail, but this video would get a little bit long. But it basically, everything is more or less going to work along those lines. You can extend this out to include all sorts of functionality and keep it all fairly generic. And of course, it's important to note that we have our own build system, and it understands all this stuff. So it understands that now we're building for Win32, so it needs to go find the Win32 subdirectory under each one of these things that have per platform stuff, and it needs to build that instead of something else. So all that stuff is sort of built into the build system. We don't have to do anything special, and there's no particular effort to support this kind of split implementation system. So there we go. Hopefully that's useful, and maybe you might make use of it, and we'll see you possibly in a future video.